Okay, and before I start with my talk, let me make two remarks here. One remark is that this is work of an undergraduate student, the first author there, and he couldn't be here, so I will present on his behalf. And the second remark is that this is a short talk, so it's an advertising talk, but it's not an advertising talk for a specific method. It's really an advertising talk for a specific problem that we find very exciting and we hope that more people will be working on. So what I want to do in this talk here is I want to introduce the factored shortest path problem. It's a factored form of the shortest path problem, and I will explain what that means. I will show that it is relevant to robotics, and then I will show sort of a first approach basically as a feasibility study that shows that we can exploit the structure to solve this shortest path problem efficiently. Okay, so the agenda today is very simple. I'll make a couple of remarks about factored representation, then I introduce the problem and its applications in robotics, and then I talk about this first approach that we call factored space heuristics. So let's think about this. So we have a combinatorial problem and we want to solve it, and so we need to exploit somehow the structure to do that efficiently. And there are basically sort of two classes of approaches. There's a strong approach here for increasing efficiency, and that is to exploit the specific nature of the interaction between the variables. So we know a bunch of examples. They're listed there: polynomial time convex programming solvers, the polynomial time algorithm for 2-set, the Kalman filter. But sometimes you can't do that because you haven't quite figured out how to exploit the specific nature of the interactions of the variables. But fortunately, there's also a weaker approach. So you can also achieve efficiency by only exploiting which variables interact with each other. And that's sort of a very common approach. We have seen lots of examples for this. Again, sort of some of the examples are listed here: belief networks and probabilistic reasoning, Markov random fields and computer vision, constraint networks and constraint reasoning, and so on. And so the problem that I want to introduce here is very amenable to these approaches of the second kind. So let's talk about that particular problem, the factored shortest path problem. And in order to introduce it, what I'll do is I will first remind you of the definition of constraint satisfaction problems, and then I will build on that definition. So we all know what a constraint satisfaction problem is. So you are given a set of variables, a set of discrete domains, one per variable, and a set of constraints. Each constraint consists of a subset of variables and a list of allowed assignments of values to these variables. And then the objective is to find an assignment of values to all of the variables that satisfies the conjunction of the constraints. Right? And that's what we call a satisfying assignment. Okay, great. So in order to introduce the factored shortest path problem, I leave the definition basically unchanged. So we still have a set of variables, a set of discrete domains, and a set of constraints. But now I'm also giving you two satisfying assignments, the start assignment and the goal assignment. And the objective now is slightly different because what I want to do is I want to find a shortest path from the start to the goal assignment that moves from one satisfying assignment to the next one. Okay, that sounds sort of a little bit dreary. At least I didn't say that a factored shortest path problem is a 4-tuple. But let's look at some visualization to make this sort of a little bit more vivid. So what you see here is a constraint and a constraint satisfaction problem. It's a constraint between two variables. I'll only look at binary constraints here. So a variable x1 and a variable x2. And on the sides, I've listed the values in the domains of these variables. And then what we are looking at here is a constraint matrix. So it tells us something about the allowed assignments of values to these variables. So whenever you see a white cell here, that particular assignment is allowed. Whenever you see a gray cell here, that particular assignment is not allowed. So a constraint, right, corresponds to a factor, specific relationship between two of the variables. Here's another constraint. And these are all of the constraints in my CSP. So the CSP involves 3 variables because the second constraint here is between x3 and x2. So now, if I want to show all of these satisfying assignments, so these are assignments of values to all of the variables. So in this case, that is 3-dimensional, right? One axis for x1, one axis for x2, one axis for x3. And a white cube here says, yep, that's a satisfying assignment. In other words, an assignment that obeys both of the constraints. Now that particular space, right, has some structure. And the interesting thing is we can just view this as a path planning problem. If I give you a start satisfying assignment, that's the one in the left upper cell, the one marked S, and a goal satisfying assignment, that's the one marked T. And then the shortest path problem that we want to solve here in that particular grid, and I should mention it's a 6-neighbor grid, you can move up, down, north, east, south, and west. The problem here is find the shortest path in the 6-neighbor grid if we interpret a white cell as unblocked and a black cell as blocked. So it's a standard shortest path problem, and of course they are polynomial time solvable, but of course the size of the state space here grows exponentially in the number of variables. So how do we solve it, right? It's a difficult problem. And the idea here is that we do have these factors, right? Because the state space here has structure, and the structure is given by the constraint matrices. But the constraint matrices can also be interpreted as grids of unblocked white and blocked gray cells. And so I can just take S and project it into both of the constraint matrices, same with T, and then I can find a shortest path from S to T in both of the constraint matrices, right? And that's shown in red. And the question is, can we use searches in these constraint matrices in order to find out what the path is in the high-dimensional state space on the right? And that's of interest because I said we only look at binary CSPs, so path planning in them is very, very fast. So how do we do it? And that's basically the factor shortest path problem. I hope that after this talk, everybody will start working on it. Now, interestingly, right, why introduce sort of this as a problem if there are no applications for it? So let me convince you of this first. So high-dimensional path planning, of course, is of interest in robotics. So I show you here a slight abstraction of a real problem in robotics, namely, how do we move snake robots? So what you see on the bottom in green and yellow is a snake robot. To the right, we have the head. Then the other green dots in the middle there, these are sort of intermediate body parts. And then the very left, we have a tail. Now, I will assume here that every body part can move independently, subject to some constraints, and only one of the body parts will move at a time. Now, there are some constraints, right? 2 body parts cannot be in the same cell, for example. A body part cannot be within an obstacle, these gray cells there. And also, body parts are linked with each other. These are these yellow connections. They can shrink and expand, but they can only expand to a certain length. And of course, these connections also cannot intersect with an obstacle. Slight abstraction, but realistic. And so now we want to get the snake robot from the bottom to the configuration shown on top, where the head is in the upper left corner, and then the 2 intermediate body parts, and the tail is the 4th X that are shown there. So let me show you how that looks like. So here's now an optimal solution. And we want to use sort of path planning, to find that particular solution. And what's interesting here is that this is directly a factored shortest path problem, right? Because the body parts can move independently, but there are constraints between neighboring body parts. So if we have a solution to that particular problem, we can employ it directly. Okay, great. So let's talk about what has been done in planning, on factored planning. And there's a bunch of work in ICAPS, not all of which, of course, applies to this particular problem here. There's much less work in robotics. So there was a couple of papers, a while ago, for example, on factor-guided motion planning for robot arms. But also there's always sort of this exponential component in there. So we want to be as efficient as possible in terms of solving, these kinds of factored planning problems. So remember, this is work by an undergraduate student, and so the undergraduate student looked at this and said, well, I don't know, how to use the information on the left, to plan efficiently on the right, but there's sort of an easy approach, and that is we just use A star on the right. Of course, that's not very efficient, high-dimensional state space, but if we had good heuristics available, right, that might be doable. Now, where do we get the heuristics from? And so you said, well, maybe we can look on the left to find out what these heuristics should be. So in particular, if we look at the path length in the two constraint matrices on the left and we add them up, and that's a lower bound on the path on the right that we want to find, then we could use information from these constraint matrices, right, from the path in the constraint matrices as a heuristic for the A-star search on the right. But of course that's not the case, because if on the right, let me see whether I can use this thing, can we see this? Yes. So if on the right, the path changes the value of x2, say from 0 to 1, there are two places on the left that could correspond to this, and they both correspond to this, right? I mean, it could be this place here and this place here. So if we add up the path length, right, we would count two moves here where there's only one corresponding move on the right, and we just overcount it by one. But one way how you can do it, right, you can say, well, the problem of this is that x2 shows up in two constraint matrices, right? So every move in one of the constraint matrices, like this one here and this one here, that changes the value of x2, we should only count 1/2, right? And then we add 1/2 plus 1/2, right? That's a move, so we don't overcount. On the other hand, if we look at x1 shows up in only one constraint matrix, this one here. So a move that changes the value of x1, like this one, that should count 1. We will not overcount because there cannot be a corresponding move in the other constraint matrix. So if we weigh moves differently in these two paths in the constraint matrices, then I will be able to get a lower bound for the path length on the right, and that means I will be able to obtain consistent and admissible heuristics. So very straightforward, and of course it does help. So here's sort of an A-star search. We look at the number of node expansions, for our snake robot problem. If we use the Manhattan distance as a heuristic, it's about 40,000 node expansions. If you use the heuristic that I just told you about, we can go down to 1/4. Now, the reason why I'm very excited about this, and there are sort of more experimental results in the paper if you want to have a look, and they prove that you can get a consistent heuristic. But the reason why I'm excited about this is because it relates to recent work in planning, in particular by Florian Pommerening, on cost partitioning, right? So he looked at planning problems, symbolic planning problems. But if we look at this in our context, right, one of the things that he says, for example, says, why do you split it into 1/2 and 1/2, right? I mean, we can split this differently, maybe in 3/4 and 1/4. And in the context of planning, he has sort of a method that gives us an optimal partitioning, which would result in the sort of most informed heuristics, if you want to, in this case here. But again, right, I mean, this is not a talk about methods. This is really a talk about a problem. And so let me summarize here, right? I mean, so the idea here is that I wanted to tell you about this factored shortest path problem. It has a specific structure. I think it can be utilized in many different ways. The problem is relevant in robotics. We showed that the structure can be utilized in the context of these heuristics, but what we are really interested in is we want to exploit the factorization of the search space directly in the search framework rather than in the creation of the heuristics. And if that can be done, we feel that would lead to very efficient search algorithms. Okay, so let me stop at this point and see whether there are any questions.
Hi, thanks for the talk. I was wondering, you have binary constraints, right, in your mapping problem, and you also have binary values. Is that true?
No, I mean the constraints had lots of different values, right? If it had been binary values, then we would have constraint matrices that are 2 by 2.
Sorry, can you?
So I said, look, if the values in the CSP had been binary, then a constraint matrix, like you see in the upper left there, would be 2 by 2, right? 2 values times 2 values. So no, I mean in this case, the values are not.
Okay, right. Yeah, thanks. Okay, yeah, because otherwise it would be very easy.
Agree, it would be a very easy problem. Solving the CSP would be an easy problem, right? Yeah. Polynomial time. And I mean, yeah. Let me stop here.
And thank the speaker again.
Thank you.